cosmic microwave background radiation, or CMB, is a cornerstone of modern cosmology, providing a window into the early universe's conditions and evolution. Discovered accidentally in 1964, its study has revolutionized our understanding of the cosmos, confirming key aspects of the Big Bang theory and revealing profound insights into the universe's structure, age, and composition. This essay aims to comprehensively explore the CMB, detailing its discovery, properties, significance in cosmology, and implications for our understanding of the universe's origins and evolution. Discovery and historical context. Early investigations. The origins of CMB research trace back to the mid-20th century, when astronomers began searching for evidence of the Big Bang theory, a model proposing that the universe originated from a hot, dense state approximately 13.8 billion years ago. Earlier theories, such as the steady-state model, posited a static and unchanging universe, prompting scientists to search for observational evidence to distinguish between competing cosmological theories. Penzias and Wilson's discovery. In 1964, Arno Penzias and Robert Wilson, working at Bell Laboratories, inadvertently discovered the CMB while investigating microwave radiation using a sensitive radio antenna. They detected a faint, uniform background noise originating from all directions in the sky, which they initially attributed to equipment malfunction. Subsequent analysis and collaboration with cosmologists, notably Robert Dicke and Jim Peebles, revealed that the detected radiation was residual heat from the Big Bang, a remnant of the universe's infancy. So, let's dive into the properties of the cosmic microwave background radiation. Now, let's talk about the Blackbody spectrum. The CMB exhibits a nearly perfect blackbody spectrum, characterized by its temperature of approximately 2.725 Kelvin, which is about minus 270.425 degrees Celsius or minus 454.765 degrees Fahrenheit. This uniform temperature across the sky implies that the CMB radiation originated from a homogeneous, isotropic source, a critical confirmation of the Big Bang theory's prediction. Moving on to anisotropies and small temperature variations. While the CMB is remarkably uniform, subtle anisotropies or small temperature variations have been observed. These minute fluctuations, on the order of microkelvins, provide crucial insights into the universe's early structure formation processes. They reflect density fluctuations in the primordial plasma, which eventually evolved into the galaxies and large-scale structures observed today. 2.3. Polarization of the CMB. Polarization measurements of the CMB offer additional information about the universe's early conditions. Polarization patterns reveal the orientation and structure of primordial gravitational waves and magnetic fields, providing insights into inflationary cosmology and the early universe's dynamics. 3. Cosmological significance. 3.1. Confirmation of the Big Bang theory. The discovery and characterization of the CMB provided compelling evidence in favor of the Big Bang theory. The uniformity of the CMB's temperature and its blackbody spectrum align closely with theoretical predictions, supporting the idea that the universe began as a hot, dense state and has since expanded and cooled over billions of years. 3.2. Age and size of the universe. Measurements of the CMB's temperature and anisotropies yield precise estimates of fundamental cosmological parameters, such as the age and size of the universe. By analyzing the CMB data alongside other astronomical observations, scientists have determined that the universe is approximately 13.8 billion years old and has a flat geometry on large scales. 3.3. Large-scale structure formation. Fluctuations in the CMB's temperature provide insights into the seeds of cosmic structure formation. Over billions of years, these small density variations grew under the influence of gravity, eventually forming the vast cosmic web of galaxies, clusters, and voids observed in the present-day universe. 4. Instrumentation and observational techniques. 4.1. Cosmic Microwave Background Observatories. Advancements in observational technology have enabled increasingly detailed measurements of the CMB. Notable observatories and experiments, such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite, have mapped the CMB's temperature and polarization with unprecedented precision. 4.2. Experimental challenges and innovations. Observing the CMB poses unique challenges, including mitigating systematic errors, reducing instrumental noise, and accounting for foreground contamination from sources such as galactic emissions and extragalactic radio sources. Innovations in detector technology, data analysis techniques, and space-based observations have significantly improved our ability to study the CMB's faint signals. 5. Implications for fundamental physics. The CMB provides constraints on fundamental aspects of cosmology, including the nature of dark matter and dark energy. By integrating CMB data with observations of galaxy clustering and supernovae, scientists have refined our understanding of these enigmatic components, which collectively comprise about 95% of the universe's total energy density. Primordial gravitational waves imprinted on the polarization of the CMB offer insights into the early universe's rapid expansion phase, known as cosmic inflation. Detection of these faint signals would provide direct evidence supporting inflationary models and deepen our understanding of the universe's earliest moments. Future directions and challenges. Next-generation CMB experiments. Future CMB missions, such as the Simons Observatory and the Cosmic Origins Explorer, aim to further enhance our understanding of cosmology by mapping the CMB with higher resolution and sensitivity. These experiments will probe deeper into the universe's origins and address remaining questions about its structure and evolution. Multimessenger Cosmology. Advances in multi-messenger astronomy, combining observations from CMB experiments with gravitational wave detectors, neutrino observatories, and optical telescopes, promise to unveil new insights into cosmic phenomena and test theories of fundamental physics on multiple scales. Conclusion. The cosmic microwave background radiation stands as a cornerstone of modern cosmology, offering profound insights into the universe's origins, evolution, and fundamental properties. From its accidental discovery to its role in confirming the Big Bang theory and informing our understanding of dark matter, dark energy, and inflationary cosmology, the CMB continues to shape our view of the cosmos. As technological advancements and observational techniques progress, future studies of the CMB promise to unlock new mysteries and deepen our knowledge of the universe's complex tapestry.